So our next speaker is Manoj Prabhakaran. He's a professor at IIT Bombay. And before joining IIT Bombay, he was at UIUC for quite some time. And he returned India for good. As a student, I have been following his work, and still today I look up to his works. They're all great. And I'm really happy that he agreed to speak in this workshop. So today he is going to talk on zero communication reductions.
Okay, thanks Arpita. Thanks for inviting me here, and thanks for organizing this event. Thanks everyone for coming for the talk. So this is some recent work with Varun Naran, who is somewhere here, and Vinod Prabhakaran at TIFR, and I'm at IIT Bombay. So I'll try to tell you what this thing is. Okay, so maybe I'll start off with kind of jump into the definition a little bit. So think of two parties, Alice and Bob, who don't talk to each other, maybe because they can't speak yet, and so they don't communicate, and they want to compute a function. I don't know why. Sorry, I have a 1-year-old kid, so I was wondering why you would want to do this. But so they get these inputs x and y, and they want to compute a and b such that this function gives you two outputs. So clearly, this is not going to be very possible if they don't coordinate at all, and if f has any sort of it's a non-trivial function which mixes x and y. So we allow a little more. There is a predicate. There is something a little box they can send some inputs to, and this box will say yes or no, okay, accept or reject, and we want their outputs to be computing the correct function only if this box accepts, okay, and if the box rejects, then you don't require any correctness guarantee. Of course, for that to be meaningful, you would require that the box accepts with some probability. So the box just gets this u and v. It doesn't see their other things unless they send it to the box. And if it accepts, it should be correct. Otherwise, we don't care. But it should accept with some probability 2 to the minus mu. Now that's a basic definition of a zero communication reduction, and we'll see why it's interesting. But it gets more interesting when you add some security requirement. So this stands for weakly secure zero communication reduction. So we'll have one more notion of security, but this is a weaker one. This one says, imagine an adversary who sees the answer from this box, okay, whether it's accepted or not, and it should learn nothing about x and y just by looking at this answer. Okay? So x and y are arbitrary inputs, not uniformly random or anything like that. The adversary should have no idea what this x and y is, or should not learn anything more about what x and y is by observing what the outcome of the box is. And there's a stronger version, secure ZCR, where it's in the more in the flavor of MPC, where you think of an adversary who corrupts one of the parties, either party. So it sees x, it sees there's not much more to see right now. It sees the randomness of this party, sees u and a, and also sees whether it accepts or not, whether the box accepts or not. It doesn't see anything on this side, right, if it corrupts Alice. And still it should not learn anything about y other than what is revealed by f of xy. Okay. It might learn a little bit about f of xy already, right? It sees this is accepting and the answer is a, then it has some idea what y is. So we allow the adversary to learn f of xy, but it should not learn anything more. So it's in the style of MPC. So this thing is called the first one here, it's called a mu ZCR from the function f that you're trying to compute to the predicate phi. Okay. You can do a little bit already with this, but the more general notion we have also allows the two parties to be coordinated using a correlated random source. So psi, which sends some value r to Alice and s to Bob. Okay, and the same, security conditions are the same, right? In particular, so this is only interesting or it's more interesting in the secure ZCR. In the other versions, this could be just a common random string that be just as good as anything else. With the strong notion, it does make a difference what correlation you have. Now, this kind of definitions of zero communication reductions or zero communication protocols have been there in the literature, not in the cryptography literature so much, but in the communication complexity literature. And I came across this kind of things in this paper by Kennedys et al. From a few years back at Fox 2012. And they attribute this flavor of definition to Gisin and Gisin on some quantum communication complexity question. Okay, so this is a little more formal definition. So in the MuZCR now I have the psi also, and the two conditions of the adversary should learn nothing if it sees whether you accepted or not. That's a weaker security. Basically says the acceptance probability is independent. It's a fixed number. It's independent of x and y. And the other one has a simulation-based definition. There's a simpler definition, and this is all perfect correctness and perfect security. You can relax it to statistical correctness and statistical security, and the definition does get a little hairier, but basically there's a definition. Okay, so since SCCR is a little tongue twisting, I'm just going to call it CSIR. Okay, so that is secured version of CSIR. The weakly secure version will be a little less secure, fewer guards. So I'll have these icons once in a while. It's the same. Yeah, it's just that it looks bigger because there are fewer guards around it. Okay, to give a little bit of flavor. So we'll see the connections and why we are interested in. There are some implications to other primitives and lower bounds. But to get started, here's a very simple instance, so that it's clear that it's not a trivial, or it's not an impossible notion. So suppose you want to compute any function f. There is always a W Caesar in which the the correlation is a common random string, and your mu is related to the input domain size. Okay, so what is the protocol? It's very simple. In the sky, you have a pair of candidate inputs, x star and y star. What Alice and Bob do is they look at their own input, and if the input matches what's in the sky, then they send 1 to the predicate. So if both parties send 1, that's when the predicate accepts. It's an AND predicate. Okay, and what do they output? They output f of, they both just compute f on x star y star. Okay, so if the predicate accepts, indeed what they're outputting is f of x, y. So, and why is it, so that's why it's correct. Why is it weakly secure? Because the acceptance probability acceptance happens when x equal to x star and y equal to y star. This happens with probability 1 over the domain size of x. This happens with probability 1 over the domain size of y, and independent of what particular x and y it is, right? Because this is being chosen uniformly at random. And the adversary doesn't see that, it only sees the acceptance probability. So that doesn't reveal anything about x, y. Okay, yeah, so that was weak. Okay, so why do we care about something like this? So we have a few applications which kind of motivated this problem, and then we came up with this notion. So okay, maybe before the applications, it's a kind of a tradition in theoretical cryptography to come up with the simplest, cleanest notions of secure computation, which capture some non-triviality already, so that you can study its implications, efficiency, and things like that. And one such notion was introduced by Feige, Killian, and Nauer way back in '94, called the private simultaneous message model. And you could think of this as another model, similar flavor. Okay, so this thing has implications to PSM model, something called, something that Yuval and his co-authors introduced again several years back, 20 years back, called conditional disclosure of secrets, and also to secure computations, MPC, or two-party secure computation, as we saw yesterday, yes. Where OT stands for oblivious transfer. So if you have oblivious transfer, as a correlation or as an ideal black box, you can do secure two-party computation without any other computational hardness assumptions. And the complexity measure here is how many oblivious transfers do you need to compute a certain function. And for these other primitives, it's about how much communication do you need to securely compute. Okay, so we get upper bounds for all these primitives. Even though they're all somewhat different from each other, we have one little thing which can give, which kind of connects everything. And that upper bound is not particularly good. It's pretty, you would hope to have much better upper bounds. It's exponential in what's called the information complexity of the function. So when you have a two-party function, there is some notion of information complexity. I'll briefly mention it later. And our upper bounds are exponential. Even though it's pretty bad, it works for every function. And we didn't have these kind of upper bounds in many of these cases. Okay, so that's the upper bound side. On the lower bound side, what we are really interested in, what we originally wanted to do was to get lower bounds for OT complexity, oblivious transfer complexity. We unfortunately don't have any new concrete lower bounds, but we do manage to recover known lower bounds, okay, using more a different technique, right, to this approach. And somewhat interestingly, we can also give a very a linear algebraic tool for potentially discovering better oblivious transfer complexity lower bounds, and it would also have implications to circuit lower bounds. So if not discover explicit examples, at least give existential results about OT lower bounds. And I hope there is something that can be done with those tools.
This conjecture imply lower bounds for explicit functions?
No, so the conjecture is saying something exists, but if you give explicit example to prove the conjecture, then you would get explicit circuit lower bounds. Okay, but since we are kind of coming up with a new thing, there are several simple basic questions that need to be answered first. So we have a bunch of those things. So the quantities of interest in these zero communication reductions are, one is mu, the acceptance probability. So the mu is the negative log of the acceptance probability. So if you have, because 2 to the minus mu is the acceptance probability, right? So mu being larger is worse, as in it's less accepting. And what we would like to have is mu closer to 0. And also the phi and psi, the particular predicate and the correlation you're using, we would like them to be simple or small. So their complexity is also of interest. Okay, so what can we say kind of right off the bat? So we can get, so we already saw this actually. If we are given CRS, then any function has a reduction, a weak Caesar reduction to and this is a mu. We'll improve this in a bit, okay, and that'll give us a connection to information complexity. But this is the basic thing you could try to say. So that is weak. If you want full-fledged Caesar, then we can't use and, okay, in general. But for every function, there is some predicate which can give you a Caesar. What is that predicate? So this just checks if it takes an input and output from Alice, an input and output from Bob, and just checks if the outputs are consistent with the inputs. Okay? And this is indeed tells you what the protocol should be, right? This is what Alice and Bob could do. but if you you have to be careful to make sure that it's not revealing anything about the other party's input other than the fact that AB equal to f of xy. Okay, so this works out to be secure. And in this case, acceptance probability is depends on the outputs, how large the output space is. Okay, so this is again something very trivial. You can also do the same thing, but instead of changing the predicate, keep the predicate as something standard, something simple. So and change the correlation. Okay, and basically the correlation now outputs candidates of input output, and that also works. Similar ideas before. Now, why did I for the Caesar, the stronger version, why am I not giving you just something which uses something simple like a CRS as the correlation and something standard like and as a predicate? And the reason is it's impossible in general. Okay, so we can show that such a reduction exists if and only if f has some very simple structure. I'll skip what this definition is, but this is a definition we used in characterizing which functions are complete, for instance. So complete is, so oblivious transfer is complete. If you are given oblivious transfer, you can compute any function, complete for secure two-party computation. Simple is essentially the definition of which ones are complete, or not being simple is the definition of which ones are not complete, and those things cannot be, do not have a reduction to AND using CRS. How about instead of AND, if I give you XOR, then it gets even simpler, or things that you can do are even simpler, essentially only things which are like XOR. Okay, you don't have to read the exact formulation, but the point is that AND was letting you do a little more than XOR actually, but even AND is not letting you do everything. And one more, maybe I should mention, we will see something which is complete eventually, right? So that will be our kind of lower bound connection will come by saying that if instead of AND I had something like OT or many OTs, then you can do everything. Okay, one more thing that is simple, basic, is consider a function which doesn't have inputs. What's a function which doesn't have inputs? What's it doing? It's just sampling outputs. So these functions need not be deterministic functions. We allow randomized functions, and so an inputless function is basically sampling a correlation. And those functions also have, they can all be, I already said anything can be computed given a predicate that is tailor-made for this. That's true even for randomized functions. And how well can you do it? The best you can do is given by how independent this correlation is, how uncorrelated the correlation is. So you can come with a measure of how correlated it is, and you can get, this is a right measure for this problem because that's the best mu you can get. Okay, so a measure of productness or how independent the correlation is. Okay, so the basic things out of the way, let me try to tell you maybe the more interesting connections. So there are these three objects which I already mentioned. So OT complexity is the number of oblivious transfers you need to securely compute some function f. Okay, that's the OT complexity of f. We typically work with, there's a wide open question. We don't have very good answers here. The question was explicitly posed by Beamel and Malkin, but maybe the fact that you can use OTs to compute was already known, so maybe something that people should have wondered about already, but they explicitly asked this question, and they gave some lower bounds, and those are the ones we will rediscover. Okay. The other thing is this PSM protocol. Okay, so let me just define what PSM protocol is right now. Yeah. the number of OTs you need. That's how many OTs do you need to compute F? Is F's OT complexity, the minimum number of OTs. Oh, the lower bound is very, it's basically the communication complexity, or in a more restricted model even. But let's say, that's but we expect that to be much higher. The upper bounds are super polynomial, or, so Yuval and others have a paper on the best results on getting, using PIR protocols. For every function, you can compute them using 2 to the square root n kind of OTs when n is input, number of input bits. So that's the upper bound. The lower bounds are lower than n, or basically n.
I think we have a barrier because there's a two-way relation with Swiss over PIR and Swiss over the codes up to some technicality. So it would seem like the answer to this question for the worst case functions is like the answer to the question.
Yeah, your upper bound is probably.
The log of the length of the best free query like in code, this is likely to be the right answer to the question, and if we're stuck, the complexity will be stuck on proving low bounds for free query like in codes, then for the same reason it's stuck.
Yeah, so this is a problem which is hard, right? Improving on the lower bounds and the upper bounds. I mean, it's also pretty hard for worst case functions. But we can give connections. We can give, so we will relate CCR complexity to OT complexity. Okay. And you'll also see CCR, I mean, you already saw CCR is a very simple object. Compared to OT complexity, we're talking about parties talking to each other in a round by round, right? So in that sense, there's a simpler problem you're coming up with. Well, it's apparently simpler problem. Okay, the other one I mentioned, the PSM protocol. So what is the PSM protocol? There are 3 parties, Alice, Bob, who have inputs X and Y, and some party, Carol, who wants to learn the output, who wants to learn f of x, y, and we don't want her to learn anything else. The private simultaneous message part is that all that Alice and Bob are allowed to do, they cannot talk to each other. They just simultaneously send a single message to Carol. Each of them sends a single message to Carol, looking at their input and a common random string that Carol doesn't see, only Alice and Bob can see. Okay. And what is the communication that's needed in the single message? How much communication do you need? That's a PSM complexity. CDS by Gertner, Ishai, Kushlertz, and Malkin, right? They define conditional disclosure of secrets. So Alice and Bob have a secret S, they both know it. It's secret from Carol. And they also have some inputs X and Y, which Alice only knows her input, Bob only knows his input, but Carol is already is holding X and Y. She already has X and Y. So only S is secret from her. And like in the PSM protocol, Alice and Bob are allowed to just send a single message to Carol, possibly coordinating with each other using a common random string that Carol doesn't see. And the game here is that Carol should learn the secret if and only if f of x y equal to 1. Carol already knows if f of x y equal to 1 or 0, but Alice and Bob do not. Okay, so they want to kind of magically disclose the secret to Carol, conditioned on f of x y equal to 1. If f of x y equal to 1, she should learn, and otherwise shouldn't learn. So this two-party, so that's, we barely understand the two-party setting in this case. So, okay, so let me start with a simple protocol that Feige Killenauer gave for PSM. The protocol itself is not very relevant to the rest of what I'm going to talk about, but it's good to see is because we use this thing as a black box flow. So this is a PSM protocol for AND. So Alice has a bit, Bob has a bit, and Carol should learn the logical AND of the 2 bits. And there's common randomness that Alice and Bob can see and Carol cannot. What is it in this protocol? So consider a 3-digit alphabet, or alphabet of size 3, 0, 1, 2. And what is in the common random string is a random permutation. So it would read 0, 1, 2, or it could read 1, 2, 0, or 2, 0, 1, or one of those 6 possibilities. So one of those 6 possibilities is written in the common random string. And what is the protocol? So let me call that ABC is the permutation in that order, right? 0 is mapped to A, so forth. Okay, so here's the protocol. If Alice looks at her input, actually both Alice and Bob, if their input is equal to 1, they will send C to Carol. Okay, so their input is 1, they both would send C. If Alice's input is 0, she will send A. If Bob's input is 0, he will send B. Okay. And what does Carol do? If she gets the same digit from both of them, she will output 1, and otherwise she will output 0. So if you look at it, if this is the only case where Alice and Bob will send the same digit, namely C. Otherwise, they will be sending either AB, AC, or BC, right? And in those 3 cases, the output should be 0. But it's not just correctness. Carol also learns nothing else, because this being random, what she's anyway going to see when they are not both sending the same digit is just 2 random characters coming. Okay, so she cannot tell if it is 0, 0 or 0, 1, for instance, the inputs. And it's a very simple, cute protocol. So we spent quite some time thinking about this, and we now know that it's optimal in all settings, so all parameters. So the message, the alphabet size that Alice should use to talk here, Bob should use here, the common random string that they should use, all of this you cannot go below what 5 gigabit did. And this was in this year, last IndoCrypt, this last piece of this question. Work with bunch of people, including Vinod, who is a co-author in this. Okay, so that's a very simple PSM protocol. 5 gigabit also had, since then there have been other interesting PSM protocols, but I want to start off with a simple protocol which seems to have not been noticed before, except Eyal told me he had thought of this at some point, but it's not been published before, I should say. Okay, so if you're given a function f, a 2-party function, you can write down its truth table. So each color here, so each row and column corresponds to Alice's inputs, Bob's input, and the color corresponds to the output value. So let's say this is a output alphabet size, whatever number of colors are here, 4, I guess, or whatever, right? 5. Okay. Sorry, 4. No, there are 5. You can have it forward, right? Yeah, I think there are only 4. Okay, I keep double counting the colors. Okay. If you are colorblind, don't mind. Don't worry, the colors don't matter. But the point, what I've done here is I've tiled this table, the truth table, with these boxes. These rectangles are tiles. They need not be contiguous rectangles. They are rectangles in the sense they are a subset of x cross subset of y. That's a rectangle. And in this case, I'm using how many rectangles? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Using 10 rectangles. There are only 4 colors, but since the way the colors show up in this thing, maybe I cannot do better. Okay? So my goal in tiling is to use as few rectangles as possible. Okay. Okay, suppose somebody has given you a tiling, maybe the best tiling for this function. We can use it to get a PSM protocol as follows. So the common randomness for this PSM protocol is going to be a random permutation of these 10 tiles. So numbers 1 to 10, randomly permuted. That is our common randomness that Alice and Bob know. And further, so there are these 4 colors. Alice and Bob, say, let's say you think of it as a 2-bit color. They each have a 2-bit share to represent the color. Okay? So something as big as a color's alphabet. So it's a secret sharing of the color for each of these 10 tiles. Okay, so 20 bits from the secret sharing, and then log of 10 factorial for writing down the permutation. That's the amount of randomness in the common randomness. I think not. So it's
Generalize it so that every point is covered by the same number of tiles.
yeah, you need to do something more. Yeah. So maybe, quite possible. This is not the optimal protocol. So they also have a little bit more randomness. They have random tape for doing a PSM protocol for ANT. A single bit, many ANTs. Okay, so they have. Okay, what's the protocol? Pretty straightforward. So they go through each tile 1 to 10, but in this permuted order. And for each tile, Alice and Bob will tell Carol if they both are on the tile. Okay, so Carol only learns there's exactly one tile around here which is in which both Alice and Bob have their inputs falling, right? And say that's the third tile in the random permutation. So in the third iteration of this loop, this AND will turn out to be 1. Carol will see that. In all the other executions, it will come out 0, but she wouldn't know anything more other than the fact that that's not the tile. And the one in which it is, Alice and Bob will be sending, Alice and Bob will always be sending whenever they fall on, whenever their input falls on the current tile, or current segment on their side, the X subset, Alice will send her actual share that she got in the common random string. Otherwise, she will send a random share. Okay, and Bob does the same. So in this case, they are both sending their correct share. Carol knows that, and she can reconstruct the color. In all other cases, she knows one party is sending their correct random share, the other party is sending a random thing. So Carol knows that what she's seeing is just 2 random strings. Okay, so she learns nothing. So the permutation is used in you go through every permutation, every tile. It doesn't really matter. It's probably all that matters is that this particular tile appears at a random position. So maybe cyclic permutation will probably be sufficient. Okay. Okay, so this is a PSM protocol, but its complexity depends on the number of tiles, right? And what we have is to do better than that. We don't need a tiling. We can use some sort of an imperfect partition, and in this case we won't have the permutation. So here we actually got a full-fledged PSM protocol, right? There was no it's perfectly secure, perfectly correct. What we are going to do here won't be a full-fledged PSM protocol. We'll see there will be a statistical version. But let me first tell you what this partition complexity is. So there is again there are tiles, but instead of choosing a tiling that fits, you are allowed to choose many tiles. They could overlap with each other. So you pick weights for the tiles. The only requirement is your tile should be monochromatic. You cannot have a tile that fits here, right? So tiles are, you look under the tile, it should be monochromatic, but tiles can overlap, and the tiles have weights on them. And the requirement is every position xy should be covered with weight exactly 1. Weight, all the tiles on top of it should add up to weight 1. And your goal is to minimize the total weight of all the tiles. So if you had one huge tile fitting here, that would have been nice. You can just have total weight 1, but typically not, right? So there will be a lot of overlap, and overlap, or you can not overlap but use several tiles. In either case, the total weight of tiles will grow, right? So your goal is to minimize the total weight of all the tiles you use. And that's, let's call it the partition complexity. It was defined by Jane and Clark in 2010 in a communication complexity problem.
Well, this is almost the same as taking the previous level of perfect tiling and requiring that it won't be covered by the same number of tiles. If you allow a multi-set Right, because you can just duplicate it.
Yeah, essentially that's what's going on. You're allowed to have everything being. I don't think real numbers will be needed. Rational numbers would probably suffice. So, but there's the definition of the. Or there's one way to define it. There are other ways to define it also using linear programs. Okay. Actually, we know some other ways of defining partition in terms of information complexity also. It's a very, very interesting object. You can think of it in several ways. And here's another way to think of it. As it turns out, there's a one-to-one correspondence between this partition and a weakly secure Caesar to AND. Okay, so even though we we have a notion of security, we had no notion of tiles or complexity measure. Well, we have some complexity measures. So the best mu you can get corresponds to the best tiling you can get. You can go back and forth between tiling and weak Caesar. So I think that's an interesting thing, but it gets more interesting. There's an object called, or there's a notion called a relaxed partition defined in this paper of Candice et al. I mentioned in the beginning. And it turns out that they relax it in some way, and I'm not going to go into the details, but that would correspond to a relaxed notion of WC, a relaxation in the sense of it's a statistical notion. So the definition I had originally was a perfect security notion. You allow statistical error that corresponds to the relaxation here, and they are the same object. Okay. So that means we can use what's known about relaxed partition to get better WZer. So if you are paying attention, I started with PSM, now I kind of drifted on to WZer. We'll come back to PSM in a bit, but this, or rather we come back to PSM here. So I will show in the next couple of slides that you can get PSM complexity to be related to WZer. If I give you a WZer with a small mu, a very good acceptance probability, then you can get PSM complexity to be correspondingly small. Okay, I've not shown that, but I'll show you that. So that's why I started talking about WZer in the middle of talking about PSM. And what do we gain by relating, so PSM complexity is upper bounded by WZer. WZer is the same as a relaxed partition, but there's one more connection. The relaxed partition is upper bounded by information complexity, or what's called internal information complexity. If you follow communication complexity literature, things that used to be done using very subtle or complicated combinatorial arguments, a lot of those results are subsumed by these information theory tools now, and specifically what's called information complexity. There are different variants of it, and this was defined by Chakravarti et al. In 2001, and Barrios et al. Gave further definitions. I think internal information complexity is defined by Barrios et al. And so now we have a connection, right? So now we have that PSM complexity is upper bounded by an exponential quantity in the information complexity. Okay. I'm hiding, there are relations to epsilon, the relaxation and the statistical error. I'm hiding that for now. Also, trivially, PSM complexity cannot be smaller than communication complexity, because after all, you're doing a distributed computation task in PSM. So, and communication complexity is lower bounded by information complexity. That's what's interesting about information complexity. So put together, we get this kind of exponential interval in which we can place PSM complexity, or statistical version of PSM complexity. It's between information complexity of the function and 2 to the 2 to some constant information complexity of the function. Okay. All right. So that's our main result in the upper bound side of things. I should tell you how we get this part. Right. So everything else is what's on the slide. I didn't tell you how you can relate WZZ to PSM. Okay, so PSM from WZZ. I'll do it in a couple of steps. So first I'll give a simpler version where I'll not get a full-fledged PSM. I'll get what I'll call a partial PSM. By partial, I mean Carol doesn't always get the output. Most of the time she'll just abort. But sometimes, whenever she doesn't abort, she will have the correct answer. And she will never learn anything. The privacy is always guaranteed. It's just that the functionality, the correctness, the completeness works only with some probability. Okay, that's what I mean by a partial PSM. And suppose you're given WZZ from F to some predicate phi. So what does that WZZ look like? So that's what it is. But the parties Alice and Bob would produce output locally by the F. Think of it as giving output to both parties, same output to both parties, or you could only think of only Alice getting the output. So so they are producing their outputs and they are producing this messages to the predicate, right? By the way, how am I doing on time? Total 5. Okay. No. There's no clock here, right? Okay. So what are we going to do about this thing, right? We cannot send this to Carol because that's not what we want to send. We want to get Carol to get the output, right? So we will use a PSM protocol to communicate the output to Carol. For a so PSM protocol is for some function G. What does that function do? It takes from Alice both these messages, U and A, and from Bob just V for now. And it checks if UV equal to 1, that's what the predicate would have checked. And whenever UV equal to 1, it will output A. Okay? So this is what we want to happen, right? So that Carol will get A. We don't want Carol to necessarily see other things. She shouldn't in particular see UV, right? UV by itself could have information about X and Y. So we will use a PSM protocol to communicate, for this function, PSM protocol for this function to communicate the output to Carol. Okay? And our PSM protocol basically looks like this. It's basically the entire work is happening here. Our PSM protocol should look like a PSM protocol, right? Alice and Bob don't talk to each other. They just send a single message to Carol, and that communication is actually what's happening in this function, in this kind of simpler function. That phi, think of it as AND, just taking AND of 2 bits. And so this is a very lightweight PSM protocol. The only downside is that it's very partial, right? Carol gets something only when message goes through. So if phi of UV equal to 0, then Carol doesn't get any output. Okay, but it's already doing something non-trivial. It's getting you security and non-trivial correct completeness. So why did we need this weak security? Because Carol gets to see whether abort happened or not. And that shouldn't reveal anything to her about U and V, because U and V could reveal information about X and Y. So that's why we wanted this ZSER that we are given to be weakly secure. Okay. Now, if magically somehow this kind of abort probability was not there, right? The WZZ had mu equal to 0, it was always accepting, or it was only with negligible probability that it would not accept, then both these problems wouldn't have been there for us. We would have got a PSM which is only with negligible probability it will abort, and in that case it's weak security is automatic. If you're going to abort only with negligible probability, the fact whether you aborted or not is not particularly informative about the inputs, right? So then as ZCR would have sufficed. Okay? So to get rid of get rid of this issue in particular, we'd like to somehow amplify the acceptance probability. But unfortunately, you cannot do that in a ZSER you cannot get better than, or we think, we don't have any good ways of in general amplifying the acceptance probability. Okay, especially if you think of, say, these outputs as being large outputs or inputs as being large inputs. So what do we do? Well, thankfully, we don't need to get rid of this acceptance or rejection probability for a ZSER. We can do it for a PSM protocol. Okay, so that's what we'll do. We'll run many copies of this in parallel. Okay, and we change the predicate we are going to do here. Instead of computing that G5 that was in the previous slide, which computed predicate on one pair of UV. Now this one computes UIVI, phi UIVI for all i's and picks the first position, the least coordinate, the first coordinate I, where the predicate is satisfied, and uses the output from that, gives out the output from that. Okay. If we do this repetition enough, then we are guaranteed that except with negligible probability, there will be such a predicate, that such an instance, right? So that will be accepting. And this predicate is now more complicated for sure, but it's something, say, if when phi is and, it's something we can write as a branching program of size related to n, polynomial in n, maybe even linear in n. Could ask Varun, he has worked out an explicit branching program for this, and that lets you translate result. You can use generate results about PSM to implement PSM for this protocol, for this function, if you want. Okay, or you can come up with maybe a clever PSM just for this function for the phi of your choice. But that's how we get our results. We plug in the PSM for the generic protocols from for a branching program function, and then we get this upper bound. Now, once you have the upper bound for PSM, the other cases look exactly the same, and that's kind of the maybe a cute thing about this ZSER. So you want to do CDS, not PSM. Here is what you do. You do a CDS for this function here instead of a PSM. Okay. And what does CDS do? There is also now a secret that these parties want to reveal conditionally. So that secret also goes here. Okay. But the function doesn't change. It's still this G5 still. And you get a CDS. And now I don't need a weak Caesar. I just need a Caesar because we are negligible about probability. And you want to do two-party computation. You do the two-party computation there using oblivious transfers. Okay. And all the oblivious transfers are used only here. This was a non-communicating part. And again, the function is the same. And in both these cases, you also have the partial version where you only have a tiny acceptance probability, but conditioned on accepting everything is correct and secure. You could do that also, in which case you won't need this G5 star. G5 star is, after all, pretty big, right? You have to repeat this n times n as is 2 to the mu. But if you just wanted a tiny acceptance probability, then you don't need to even do that. Okay, so these are probably not the particularly useful concrete results. PSM is the one in which we can get, I think, something. Well, maybe here also you can get something not known, but I'm not sure. Okay, so I think that's all I want to say about the upper bound side. You can do, you saw it for PSM. The other things are all similar. But maybe the interesting thing is also that they're all similar, right? There's the crux of the thing is in that zero communication reduction. Okay, so how about low bound connections? And now I'll mostly only talk about ZSER, which is the strongest version of zero communication reductions, and so the one that has the highest lower bounds, right? The most difficult thing. So we would like to relate lower bounds of other things to complexity of the secured version, the ZSER. Okay, so the main result I'll talk about in the following. is that if you have a secure two-party computation protocol using a small number of OTs, you can get Caesar with a correspondingly small sized phi OT and a correspondingly large enough acceptance probability. Except of course the acceptance probability is exponentially small in the OT complexity here. Okay, but that's kind of the regime for Caesar. Things are going to be, the acceptance probability is exponentially small, still we will get meaningful bounds. Okay, okay, so this basically I said if you have good protocols for two-party computation using few OTs, then you get good protocols for Caesar. So if you show you don't have good protocols for Caesar, so you give lower bounds for Caesar, they imply lower bounds for OT complexity. So you know this thing is it takes some work. So that's I would say our main lower bound reserve. We don't unfortunately give any new obtain any new lower bounds this way. Is it even reasonable to expect that you would have lower bounds? Maybe the Caesar is such a simple object now that they don't have high lower bounds, right? They're already easy. Well, we don't think so for two reasons, or rather, yeah, for one reason here, which is that if you have a Caesar, we cannot translate Caesar upper bounds to OT upper bounds directly, OT complexity upper bounds, but we can do that for partial protocols. So what's a partial protocol again? It's a two-party computation protocol in the context of two-party computation. Maybe most of the time it aborts. Okay, and then the parties learn nothing about each other's input. But sometimes with a positive probability it will accept, the protocol will accept. And in that case, condition on accepting, it's still secure and it's correct. And it's not clear if I gave you this freedom to abort most of the time and accept only once in a while. But condition on accepting it should still be secure. And it's not clear how that makes life any easier. It seems like it's still a difficult task to do. And it's plausible that this partial OT complexity is not much less than OT complexity. And who knows? So if so maybe there is hope that we are not losing too much by using this route to lower bound OT complexity. And finally, I'll go over all this in a bit. Finally, we do have this contrary result. I said we recover the best available OT complexity from Beeman-Markin, but it's a sublinear lower bound. And I'll try to show you this linear algebraic formulation because it doesn't quite fit in 1 minute slide, but it's not too much more complicated. Okay, so I'll start with this thing. And I'm not going to give details of any of this, just the high-level ideas. So suppose somebody gave you a two-party computation protocol which uses only a few OTs. And yeah, we want to show that we can get Caesar with a small mu, okay? Which will actually be mu, since it's logarithmic, by definition negative log of the acceptance probability. This mu will be in the same range as the number of OTs here. Okay, what's the intuition? So Alice and Bob, if they had a transcript for this execution, right? So since it's a secure protocol, somebody who looks at the transcript doesn't learn X or Y. They just look at the transcript, not the OTs that went into computing it. Okay, so all these transcripts essentially are distributed the same way, independent of the input, modulo some technicalities that I'll skip. So suppose you could sample, you are given such a transcript from that distribution, and also suppose Alice and Bob could magically get OT correlations. So R is Alice's side of OT, so 2 bits x0, x1. Bob's side of OT, S is BXB, right? Or some choice bit and the corresponding output. And this may for many such OTs, right? Suppose they could magically get these OT correlations. They are not just valid OTs, they should also be correctly correlated with the their inputs and the transcript. Then they are done. They can just locally compute the final. So they have their view, in the protocol, and they can compute the output. Okay, so how do you get, so that's a view of a party, right? It's the transcript and its side of the OT and its own input. So if you could magically get all of these things correctly sampled, you'll be done. But forget, even getting the whole thing correct, even sampling OTs you cannot do without communicating with each other. But that itself is okay. We can use this predicate to abort our invalid choices. So I pick an X0, X1, you pick your B and XB. If your XB is not consistent with my X0, X1, then this predicate can abort. So that's a predicate we will use. It checks if inputs given from Alice and Bob are consistent with, are in the support of the OT correlation. So that's not a big problem. But how about making it all correlated with, the transcript? And here there's a very useful property of protocols, not just secure protocols, but protocols in general, that the transcript, the probability of a transcript factorizes in a nice way, because transcript is produced by two parties locally doing computation and sending messages. And so in our case, the factorization is like this. So Alice has R and X on her side, and Bob has S and Y on his side. So the probability of Q given all these is factorizes as something which depends only on Alice's side of things and the transcript times something that depends only on Bob's side and the transcript. Okay, so what's that? How is that useful? So we can try to do the following. Alice would, so both of them know this Q. Alice would try to sample her side of the OT with probability that's proportional to this. Okay, this is not a probability. This is not these are arbitrary numbers. They don't sum up to 1. Their products are probabilities. Okay, but you can sample proportional to this. And similarly, Bob does it. And then you can show that the probability of this and conditioned on this R as being in the support of the OT, you can show that this is actually correctly distributed. The Q, X, Y, Q, R, S, they are all correctly distributed. Okay, so that almost works. That's what they're going to do. That's just one glitch. What you'd end up with in that case will be a weak Caesar. This abort probability will still depend on XY, or can depend on XY. So there is some hairy technical fix you have to do. Basically, they will abort with some extra probability based on their whatever local view, and kind of shave off make sure that the accepting probability is the same in all cases. Okay, so there's a little bit of loss in mu, and but you can do it. And at the end of all that, you will get your mu to be n plus m, where n is the input size, m is the number of OTs you had to pick in this way. This works, there is some caveat about which kind of functions you need, otherwise there's a little more loss. And the size of the predicate phi is, the phi is basically that many OTs essentially. And so now if you have a lower bound on mu, that translates to a lower bound on m, right? So if mu is greater or equal to t, then m is greater or equal to t minus m. Okay, so that's all I will say about the connection to OT complexity. I'll say a few things about this reason to believe question. So I probably already said everything here, but let me just quickly go over it. So I define this partial protocol as something in which it's okay to abort most of the time, as long as conditioned on not aborting, you should do fine. It should be secure, and that should happen with some positive probability. I'm not even insisting it's exponentially small. It could be even smaller for now. So partial OT complexity can be defined in terms of number of OTs required. You are allowed to use any positive probability. Our intuition is that making that smaller and smaller is not going to let you save on OT complexity beyond some limit. Okay, and why was that interesting was because we do have upper bounds, and these are translating to upper bounds in partial OT complexity. How? Without any blow up, no repetition 2 to the mu kind of repetition. That was by earlier protocols I showed, but instead of that G star we had, you just use a G, the one instance of OT, one instance of OTs from this protocol. Okay. Okay, so I believe a well accepted conjecture is that most two-party functions, or at least there exist two-party functions which have superpolynomial OT complexity. We do not know how to prove this. The upper bounds, the lower bounds are linear currently, but I would like to propose the same conjecture for partial OT complexity. We don't have any intuition to go say otherwise, but of course, who knows? But you could, while you are in the business of making conjectures, you could go even further, and you could say this partial OT complexity cannot be much smaller than OT complexity, and you could say should be polynomially related. Okay. Well, if that is the case, then this route of using these are lower bounds to get OT complexity lower bounds is not a bad idea. You're not losing too much by just focusing on these or yeah. Okay, so let me say the last thing. So how much time I have? Okay, I'll finish with like a couple of slides quickly. So the linear algebraic formulation. We define a quantity called invertible drawing. The name is totally arbitrary, but it has some connection to rank. That's why. And so here is the definition. So for any function f, you can define this matrix, essentially the truth table, but it's indexed by inputs and outputs on each side. If it's a deterministic function, it's a 0, 1 matrix. And you could also define matrices with only inputs when it's a predicate. So this has only inputs on each side, and so 1 wherever the predicate is 1. And in terms of these two things, if we are given a Z-ser without a correlation, it has a very simple structure. The whole definition can be written linear algebraically. The correctness basically says your protocol, when you write it in the appropriate fashion, should satisfy this condition. And the security, the simulation conditions also are linear algebraic. G and H correspond to some simulator's action. This strange bracket is just to say it's not exactly A and B themselves. You have to do a slight transformation to define this the simulation guarantee. But it's all very simple. Like I'm skipping the actual definition, but it exactly looks like this. And what is the rank? So I have a parameter k. So instead of one copy of phi, think of k independent copies of phi. And the question is, what's the smallest number? How many copies of this phi do you need before you can get this to work for a small enough mu? Okay, maybe even in a finite mu, but let's say for a small enough mu, which I have not defined yet. And that is, so instead of phi here, you have phi to the k. So this will become a tensor product. And one way to define this small enough is to, k and this mu are in the kind of same regime. So you could just add them and say you have to minimize this quantity. So as you increase k, mu k comes down, but what's the best you can make it? So the conjecture is that there should be some family of functions such that this quantity is superpolynomial. Okay. And if you could show this, it will imply superpolynomial OT complexity, which in turn implies superpolynomial circuit complexity. It's just an existential result. So we already know circuit complexity existentially needs exponential size circuits. But if you find an explicit example, of course, that would be a major breakthrough. All right, so to conclude, the new object, just recently born, pretty interesting stuff, does various things. cute things. And we get some concrete results also. It's not all crap. But do we have more connections that we can find? We have probably only scratched the surface. We don't understand how these things really work. But still, they are much simpler than full-fledged protocols, for instance. So they're kind of more, just one shot. There's not even any communication, right? Just one shot to the predicate, one shot message, and comes with many new things to play with. So we define this partial OT complexity, for instance. We have this invertible rank conjecture, and even just coming up with new Caesar construction, would be interesting. Okay, so I'll stop there.
Questions? Okay, so if there are no more questions, so let's break for lunch. Like yesterday, we head to CSL on, and we rejoin at 2. 1 second. I have to hand over the door. Thank you.